Just before we wrap up this whole energy concept around electromagnetic waves, let's go back and discuss the half-wave antenna that Joe had in the previous lecture. Just keep in mind though that this isn't technically accessible, but I hope it helps you realize why energy transported by electromagnetic waves is important. So a half-wave antenna is two conducting rods that are connected to a source of alternating voltage. So we have a positive conducting rod and a negatively charged conducting rod, and there's a potential difference in between them. Now, the alternating voltage accelerates charges between the two rods, and the whole reason that this antenna is called a half-wave antenna is because the length of each rod is actually a quarter of a wavelength. So therefore, the antenna is like an oscillating electric dipole. So what we have is we have conventional current or electrons that flow from the negatively charged conducting rod to the positively charged conducting rod. However, the electric field, remember from the convention that we describe electric fields, is it flows away from the positive charge and towards the negative charge. So here we have an electric field that is directed from the positive to the negative, and current flows in the opposite direction. Now, if current is flowing up the rod, therefore, using our right-hand rule, we can work out in which orientation the magnetic field is directed around this rod. So remember, we put our thumb in the direction of the current, and the direction in which our fingers wrap around the rod is how our magnetic field is directed. So here it's going to be directed in and then coming out the other side as per the drawing. Therefore, we always have a magnetic field that is perpendicular to our electric field. And now to work out the direction of energy flow, or the direction of the electromagnetic radiation from this encounter, is we have to use our right-hand rule again, remember. So we put our fingers in the direction of the electric field. We remember for our E cross B, we curl the fingers towards the direction of the magnetic field, and our thumb points in the direction that the wave is traveling. So we can see that the electromagnetic radiation is directed outwards from either side of the antenna. Now, the dipole energy dies out pretty quickly as you move away from the antenna. However, the source of the radiation found quite far from the antenna is the continuous induction of the electric field by a time-varying magnetic field, and oppositely, the induction of a magnetic field by a time-varying electric field. Therefore, when we produce these waves, they're in phase with each other, and the flow of energy is outwards at all times. And this is also why, in the first lecture, there is an orientation as to when electric fields and magnetic fields are detected by antennas. They have to be at the right, what we call polarization, or at the right orientation. So that's why as Joe rotated the antenna, he was picking up different intensities as he rotated it, depending upon its alignment with the field. So I hope you appreciate how half-wave antennas work a little bit. It's not accessible, but I hope you can see why this is so important in telecommunications.